So there are a couple different ways to validate a regression model, but why do we perform that model validation? Going back to that CRISP-DM framework, we're now looking at the point of the process where we've already made our model, and now we're looking at how good it is. So some of the ways of doing this is looking at your adjusted R-squared, one of our two information criteria, or by using an out-of-sample selection. And so one thing to remember is, if you do not remember anything else from this class, is that R-squared is a goodness of fit test. That's it. So it's looking at how closely your model mimics your data. I like to think about this as, how closely does my shoe fit my feet? So do I have a special runner shoe that has a separate compartment for each toe? Or do I have big winter boots with room for extra socks? So if we look at the calculation for R-squared, it's 1 minus the sum of our model error divided by the sum of our variance and our dependent variable squared, both of those values. So since both of these values are square, looking at this equation, we know that our R-squared value is going to be bounded between 0 and 1. And if we have a larger R-squared value, that means that if we look at that, this function right here, this portion of our function, this means that either the variance in the dependent variable is really small, or really big, or the amount of our model error is really small. So our top number is really small, or our bottom number is really big, or both, allowing for us to have a larger R-squared value. Because really what R-squared is looking at is how much of the variance in my outcome variable or target variable is explained by the combination of my predictor variables. So once you've made your model, what you're doing is you're trying to evaluate how good your model is at predicting new values. So a common error that happens with making models is that you're overfitting your values. And so one of the things you've got to think about is, with machine learning algorithms, if you leave them to their own devices, they're going to try and get the perfect value. And so when we're looking at the R-squared metric, one of the problems that we have is that when I add complexity to my model, that R-squared value is inherently going to go up. And so as that happens, I'm starting to get into this problem of overfitting my data. So the thing you've got to keep in mind when you're looking at your R-squared value is, when you're measuring your error against the data set used to fit the model, that can be very misleading. And so that ends up affecting our future performance. We've got to think about the bias variance trade-off when we're thinking about the complexity of my model. And then if I have a complex model, that gives me, if I have low bias, this means my model fit is good on my training data, but we don't necessarily know that we have anything for our score data or our validate data. Our high variance model is going to be more likely to make a wrong prediction when I have a new data applied to that model. And so some things that we can do to curb our enthusiasm is to use our adjusted R-squared value, which penalizes your R-squared value as you add more predictor variables, or you can look at two of our information criteria, or you can use out-of-sample data. So looking at our information criteria, once again, it's just another goodness of fit measure for our model, and it goes back to that idea of entropy to look and looks at the information that is lost and evaluates the trade-off between precision and the complexity of your model. Our two types of information criteria are the AIC, which is the Akaike information criteria, or we have the Bayes information criteria, or BIC. And so the Akaike looks at the quality of the statistical models in comparison to all other models. And then our Bayesian information criteria is going to be looking at your model relative to a specific set of models. And so one of the really cool things about AIC and BIC is that unlike R-squared, as I increase the complexity of my model, it doesn't really inflate these values. So that's kind of nice. If you're worried about or interested on how the Akaike or the Bayesian, information criterion are calculated. Here's a little bit of information on that so that you can kind of look at that. Another option that you can use is what we call out-of-sample data. So sometimes, especially if you have a large data set, you can use a portion of your data to make your model, and then you run your model on the remaining portion to evaluate how good your model was. And so starting out with, why do I do cross-validation? Cross-validation is a technique for assessing how the statistical analysis generalizes to data that the model has not seen yet. And so it's a technique for evaluating your machine learning techniques by training several models on some subsets of available data and then evaluating them on complementary data sets. So effectively, you're looking at how that model performs on data that the model has not yet seen. And so again, the reason we want to do that is because we're interested in how well that model will generalize to new data. And it's going to be important to detect any type of overfitting your model. So if the model is overfit, and what that means is that the data is not going to generalize well or the model is not going to generalize well to new data. And it does a poor job of predicting future observations. So again, we're looking at observations that were not included when we were training the model. This is by far one of the biggest and costliest mistakes that a company can make when they're deploying their model, is not effectively evaluating how well it would generalize onto new data. So this can be a very important step in the overall process of your data mining or analytics project. So here's an example where we're looking at what we call five-fold cross-validation. So here you're splitting your data into 5 samples. And in this case, we're using 5. So that means that you have 1 to test and 4 to train. And then you're going to fit the model with your train samples. And we're going to use the test data, to calculate our predictive error metric. And then we're now going to change which sample we use as our test set until all of our samples have been used as either a train or a test in the model. And then we take the average of each of these metrics to compute that final k-fold. In this case, it would be a 5-fold cross-validated prediction error. So here's just another view where we need to train our model. In this case, the top one we're looking at with k-fold, we're looking at 3-fold cross-validation. And again, we're using 2 to train and 1 to test. And you go, okay, well, you could do more than 10-fold cross-validation. And that's true. You can use something called leave one out or in-fold cross-validation, where in is the number of observations that you have in your data set. So let's say we have 100 observations in our data set and you do 100 folds. Basically, you're going to train your model on the 99 observations, if we assume that we have 100, and then you leave one out as your test or your validation data. Then you're going to repeat this for the next round, fitting the one observation that's left out and using the model that's built on all the other observations until you have completed all 100 folds. Then you'll just take the average of all of those accuracy measures as your leave one out cross-validation measure. So we have a couple different kinds of cross-validation. So if you use a test set, the upside of this is it's cheap. So a lot of times you'll have a test and a validation set. But it can give you an unreliable estimate of future performance. Our leave one out is very expensive in the sense that the more folds you have, the more computing time it can take. So sometimes it can take your software quite a while to go through it. But the upside of it is it doesn't waste any data at all. And so if we look at 10-fold, 3-fold, depending on the number of folds we have, if we have more folds, we have less waste in our data. But as we increase our number of folds, we're also increasing our computation expense. From a best practices on reporting, when you're reporting your metrics as measures of error, you want to use your cross-validation to find your best model. So whenever you're reporting out whatever your accuracy measure is, you want to use the measure from the cross-validated procedure, not from your training procedure. So you always want to make those decisions using your cross-validated measures. And if you're looking at regression, you're still going to report that adjusted R-squared for your model as you normally would. So there's really no change there. You're just using the cross-validation for reporting of the measures of accuracy as well as to select the model. The added cross-validation information allows readers to evaluate not just how much variance can be explained by the model, but also that predictive accuracy in your model. And remember, your good models should have high predictive and explanatory power. So if you can get your prediction, which again you would evaluate through cross-validation, as well as your explanatory value to be high, then you really have yourself a pretty darn good model. So some things when measuring model accuracy, you can determine the prediction error for each of your observations within your data set by finding the difference between the value predicted by the model and the actual value. So your mean squared error is going to be the average of your prediction errors for all of your observations. The mean percentage error is going to be the mean squared error multiplied by 100 to get your percentage. The mean absolute error is going to be the average of the absolute values of each of the prediction errors, with the mean absolute percentage error being the mean absolute error multiplied by 100. And so regardless of the measure that you end up using, better models tend to have low error values for all of these measures.